And this question we have seen that you have to calculate the SiO2 value, and which is recalculated on the volatile free basis of a rock whose measure oxide and weight percentage and composition is given here in this table. So you will have to find out the SiO2 value. For the SiO2 value, what you'll have to do is that just take this value 45.58, which will be divided by the whole, which is here as 95.72, and which will be multiplied by 100. Simple questions is that, no need to confuse with this, and whatever answer you will be getting here, that will be your answer, right? So like this you will have to solve the questions. I'm just trying to calculate it out. 45.58 divided by 95.72 and multiplied by 100, which is equal to 47.6. Why I'm not writing other digit as 618? Because it's given here only. Oh, okay, 2 decimal place, so 61. Right. So like this, you'll have to choose, right? So this much percentage is there, right? And somebody may choose from here directly that this is the answer. No, this is not answer, because you have to calculate the weight percentage among these. So like that. In the same way, there might be a questions for Al2O3. In that case, what will happen? Similar way, there will be 12.49 divided by 95.72 and multiplied by 100 again. And if you look here into this, then you'll see that what answer we are getting: 12.49 divided by 95.72, which is equal to approximately 13%, 13.04. So right. So in this way, you will have to solve the question. You can again calculate for the calcium, the sodium, the potassium, the magnesium, the FeO, MgO, CO, Na2, K2. So for all these alkali components, the silicate components, the aluminum components, right? So let's see the next here. For this, you have a formula that is alpha is equal to R standard minus R sample divided by R standard into 1000, or you might have seen the formula as R standard upon R sample minus 1, something like that. So that could be there also, right? So there are different formulas, and you'll have to put the value which is given here will be the sample value, and standard value which we are using here, that will be in sometime in the examination you might not receive like this, that use this value. That may be given in the useful table. The useful data column is there in the upper side by the I button. So wherever you will be solving, so in that portion you may get, and you will be solving the question very easily. Now coming to this, for ionic strength, this we left yesterday and we will be seeing today. The ionic strength is very simple. It's not that tough. First, what you have to do is that I'll tell you how to calculate, right? So one by one we'll be seeing. Let's calculate for NaCl. So NaCl has to be broken into the component. Then only, because if you remember that the substitutions, different substitution law was there, that the cation and anion is replacing for some other element, and they're competing for the site. So here, if you'll see, the Na will break into the Na plus and Cl will break into the minus one, right? So we're gonna do nothing with this. We just need the charge and of course the molarity. So this is I is equal to half of the summation Ci Zi square, right? Which means the concentration which is given here, molal, and the cation and anion, their square, summation of their square. So here the NaCl we'll be seeing here, this will be getting as half, molarity is 0.5 multiplied by cation, that is 1 square plus 0.5 anion, which is minus 1 whole square. So that's it. And half, here we are getting 0.5 plus 0.5, which equal to become 1, and this whole become 1 by 2, so this whole become as 0.50. So for this NaCl we have calculate, and now we'll be calculating for CaCl2. If you look into the CaCl2, then you'll see that it break into this Ca2 plus 2 Cl minus 1. Cl2, na? So Cl has to break like this. So here we'll be receiving, if you calculate for this, I is equal to half, molality here is 0.25, so 0.25, and the cation, that is 2 square plus 0.25 multiplied by 2. Why? Because this 2 will be making twice, and the square will be of minus 1, right? So here if you see, so this becomes 1 plus 1, how? 2 to the 4, and 4 multiplied by 0.25, so this becomes this much, and this becomes 0.5. So if you'll see here, you'll get as 1.5 divided by 2, which is equal to 0.75. And if you will see here, we have to sum of all these because these two gradients was there, so you'll receiving as 1.25 as the answer. Make the sum of this now, because we have to calculate combinedly for NaCl and Cl2, and here I have calculated separately for NaCl and for CaCl2, just to make you understand, right? Is there any issues? Then you may type, else we'll be moving on to the next. Be quick. So shall we move? Right. So again, there is a question of quartz sample where we have to find out the fractionation ratio. So that, hope you understand. You can solve that in the similar way. If you'll see, this will get again the same answer, and we can try this time as together. So half for HCl, that is 0.5 into 1 square plus 0.5 into 1 square, and bracket close, plus again half for this 0.25 into 2 square for CaCl2 plus 0.25 into 2 1 square, like that. So here if you'll see that, you'll got 1 plus half, here you'll receive as again 1.1 plus 0.50, sorry, I'll receive as 0.50 plus here you'll this, if you'll be solving it, this will be 0.75. Then again if you sum up, then it will become 1.25. That's your answer here. Did you understand how did we solve this? Is there any problem in this question? Please type in comment box. Be the first. Quick. No problem. All right, let's move to the next question. HCl, CaCl2, that's it's the same question. And here is the ionic strength of the solution, NaI and NaCl. So let's see, whenever you will be receiving, I'll tell you the shortcuts. When you will be receiving the same thing that is there, right? Single unit is there. Then just sum up the molarity that will be there, ionic strength. Let's see how. I'm saying the answer is 0.55 plus 0.45, which is equal to 0, 1, right? 1.00 is the answer. Let's see how. This NaI is going to break up into Na plus and Cl. Oh, sorry, I minus. So that is iodine. But this will work only when there is only single valency. If there will be divalency or trivalency is there, so that it will not be applicable, right? So for NaCl again, this is Na plus Cl minus, like this. So let's solve. Half 0.55 into 1 square plus 0.55 into minus 1 square plus half, and if you see here again 0.45 into 1 square cation square for Na plus 0.45 into minus 1 square Cl square, this becomes. And if you see that sum of these half 1.10, again this will be divided, then this will become again 0.45 or 55, and this is here, and if you'll see here, then you will get the 0.90. So this is here again answer as 1.00. If there is given as up to 2 decimal place, otherwise you can write as 1 simply, or there is no issues in writing 1 plus. Is it clear? Or any issues in this? Shall we move on to the next question? Again, I'm not going to solve this question. I'll just add up the molarity, because I know that both are having plus 1 balance or 1 balance, single balance, right? The monovalent. But yeah, here in this case, there you'll have to solve for CaCl2. Why? Because this will be twice. So this will differ a little bit. Otherwise, for this, it will be the answer. So there was a question here. A continuous sequence of 100-meter sequence was deposited in 10,000 years. That means a sequence, let's say this is 100-meter. This was deposited in the 10,000 year, right? 10,000 year time was taken here at the uniform rate. Of course, at the uniform rate. The number of samples that must be collected at equal stratigraphic interval of sample to the succession every 100 years. So question is saying, in this sequence, how many sample has to be taken that it will get the sample of every 100 years at least, equal stratigraphic interval. So we gotta do nothing with this thickness, because it doesn't matter what thickness we are taking. They have not asked that what thickness we have to take the sample. They're saying how many samples. So number of sample will be, let's see, this was deposited in 10,000 year. So we require at 100 year. So 100 sample. 100 sample has to be taken so that it will, at equal interval of stratigraphic, that is at every 100 year. Now for the garnet, and these are very basic question. This we have again solved in the last session, but we'll be seeing once again. Let's have a look here. You'll have to calculate here for the X. in the Garnet formula, FeMg in this one, and for Ca, the mole percentage of glossular, and glossular contains your Ca3, and here we have got Cax. So let's see, if you remember, then the common general formula for Garnet was something like, if I say X3 Al2 Si3 O12, something like that. So this has to be 3 whole because this is given here. So we'll see as 2.5 plus 0.3 plus x equal to has to be 3. So this becomes as 2.8 plus x equal to 3, and x equal to, it becomes 3 minus 2.8, and which is equal to 0.2. So the number of mole at x has become as 0.2, and you'll have to calculate the glossular percentage in this formula. So glossular percentage, how we will be calculating? The mole percentage which is available and the whole. So this becomes 6.67 something. Is it clear? If there is any issues, please let me know, type in comment box. So in the same way, we'll have to calculate for almandine, and in almandine, you know that we'll have to see this Fe, because Fe3, almandine have formula Fe3, Al2, Si3, O12, something like that. So here the almandine is 2.5, which has to be divided by 3 and multiplied by 100. So this will be something 83 or something like that. All right. So this is very easy. Even there may be question for Mg now, which is your pyro, and then again you'll have to see how to calculate it out, right? So these are the basic questions. Let's say 3 multiplied by 100 and something. This will be something which we'll have to calculate, right? Sorry, 0.3. This will be something 14%, right? We'll see 0.3 by 3. It will be 100% or 10%. 10%. And now there is a question. This we have already seen in the last class as well, in the yesterday, but we'll see once again. Whether dunite is comprising of pure phosphatite. First thing is that dunite is monomineralic rock, which is composed of olivine greater than 90%, right? So in the olivine, even it is composed of by pure phosphatite. Pure phosphatite. So which means that here we have Mg2, mainly Mg2SiO4, which will be divided into 2 MgO plus SiO2. So Mg2 SiO4, which means here is that 2 moles of MgO is forming from 1 mole of phosphatite, and 1 mole of this is forming by this. Because why we have break up into all these? Because we have the weight percentage only in this form. So let's see here, if you want to calculate for Mg, which means for 2 mole of Mg there will be. So let's see the weight percentage of MgO in the mad. It will be 2 multiplied by MgO divided by 2 MgO plus SiO2 multiplied by 100, like as usual. So this becomes 2 multiplied by 40.30 divided by 2 multiplied by 40.30 plus 60.08 multiplied by 100. So this becomes as 80.60 divided by 140.68 multiplied by 100, something like that. So you'll receive the percentage, which is something 47 point something percent if you'll solve about this, right? So it's very easy actually. I'm going to solve it out. 80.60 divided by 140.68 57. 57.29, right? Not 47. Once you will solve, you get the answer. Right? Here. Next question. The most abundant metal by weight percentage in earth crust is. If you see the composition of earth crust, so mainly there is silicate composition. In silicate, the most important thing is there that Al2Si3O8. Remember like that formula in the all silicate minerals? So of course, aluminum will be the most abundant metal in the earth crust, right? Getting my point or not? Based on the ideal and member formula of dioxide, the mole proportion percentage of CaO for plotting the mineral in CaO, MgO, SiO2 triangular diagram is what? For dioxide, right? So you were having here as a diagram, let's say CaO, MgO, let's say this is CaO and SiO2. This is our diagram. And you want to plot here dioxide, and in that you want only for percentage of CaO. And dioxide formula, can anyone type what is dioxide formula? Let's see how many remember. Only one. CaMgCO3. No, it's not CaMgCO3. It's CaMgSi2O6. So here, if you see CaMgSi2O6, then you will have to break it into. So this will become CaO plus MgO plus 2SiO2. Equation is balanced up. CO is having 1 mole. This is having 1 mole. This is having 2 mole. So you have to calculate for weight percentage of CO. For percentage of CO, now this will become what? CaO divided by CaO is divided by CaO plus MgO plus 2SiO2. So mole percentage is given. CO is 1 plus 1 plus 1 plus 2. So 1 by 4 multiplied by 100, which becomes 25%. So this is the answer. Is there any problem in this? Mole we have to see, na? Mole of CaO plus mole of MgO plus mole of this SiO2. How many moles are there? 2. How many moles are there of Mg? 1. How many moles are there of CO? 1 only. Is it clear? In the similar way, 25% is of MgO also. 50% is of SiO2. Was it clear? Be quick, type in comment box. All right, let's move to the next. Clear, right. Calculate the concentration of in ppm of nickel in olivine that crystallizes from basaltic magma containing 20 ppm nickel. The partition coefficient solid upon a melt of nickel is this. Let's say it is given here partition coefficient solid upon melt. So the value of this is given as 5 is equal to solid. So look here, the calculate the concentration of nickel in ppm that crystallizes. So we have to calculate in solid, that is x, and in melt how much? Sorry, 20. Originally it was 20. In solid we have to calculate how much is there, and in melt it is 20 ppm. Calculate the concentration in ppm of nickel in the olivine that crystallizes from basaltic magma, and that basaltic magma contain 20 ppm nickel, parts per million nickel. Now the partition coefficient is given here as 5, so this will be x equal to, it will be 100. Is it clear? Crystallizes, it is being solidified. So nickel is trying to crystallize with olivine because it has covalence and association definitely with this, so it has to be. Is it clear? All right, so let's move to the next. Again 2000 ppm is given. This will become again 10,000 now. Right? Simple formula. It is given here solid by melt. Again solid by melt is here. Again same thing is there. Again same thing is there. Hope you will be able to solve this question. Again same thing is there. Again same thing is there. Choose the correct zone. So zone you will have to calculate, and hope you most of you know that how to calculate the zone. This belongs to the crystallography, but we will be seeing here for calculating zone. I'll draw a simple matrix. Let's write out this one set 110 write this 2 times and write this 2 times again 010 and just exclude it out. Now at the position of, let's say, the zone are U, V and W, U, V and W. So U is equal to will be this multiplied by minus this. This multiplied by minus this will be for V, and this multiplied by minus this will be for W. So let's see here, U is equal to, it will be 1 multiplied by 0 minus 0 multiplied by 1, which is equal to 0 only. We will see that 0 multiplied by 0, 1 multiplied by 0, 0 multiplied by 0 minus 1 multiplied by 0, which is equal to 0. W is equal to, you will see is that 1 multiplied by 1 minus 1 multiplied by 0, which is equal to 1 only. So we have got 0, 0, 1 as a zone, right? Like this you will have to solve. Hope you understand that how we will be solving all these. For this again, let's say 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0. Again, exclude it out. So this becomes -1, or which is called as 1 bar. Next one become 1, and the last it becomes 1 only. So this is the join. This is basic. If you'll do the practices, you no need to see even. You'll do it directly. But try to solve in the proper manner so that there will be less chances of avoiding error, right? So this is multiplied by this minus this. So -1 will remain, +1 will remain, +1 will remain. 1 bar, 1 bar. For this, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1 bar, 0, 0. Right? Hope it's all clear. You understanding how do we are solving? If there any problem, please tell me. Clear, right? For this as well, you'll have to calculate out. Let's calculate it for this. 101, 101, 11, sorry, 011, no? 011. It is excluded out. 1 bar, 1 bar, 1. Right? 011, 011, 001, 001. 1, 0, 0. Triple 1, triple 1. 1, 1 bar, 0. Right? See how we are solving? 0, 1, 1, 0, 1, 1. 1, 0, 1, 1, 0, 1. Exclude it out. 1, 1, 1, 1, 1 bar. So the final is 1, 1, 1 bar. For this, if this will be the case, it will be 000. Right? We'll see how. 0, 1, 1, 0, 1, 1. 0, 1, 1, 0, 1, 1. 1 minus 1, 0. 0, 0, 0. 0, 0, 0. If the same phase is there, no zones can be possible. Choose the correct set of the crystal faces for C crystallographic axis as a zone axis. C is a zone. So, if C is a zone, this becomes the correct. See how? If you see the interpretation, at C axis here is 0, but here is 1, here is 0. So it's not possible. You see here is 0, here is 1, here is 0. It's not possible. Here is 0, here is 1, here is 0. It's not possible. Only the C, that C axis, it should be the same thing. Only this is there. It's quite easy actually. This we have already seen. We have done this. We have done this. No, we have not done this. When dunite comparison pure montesilide undergoes the melting, the weight percentage of MgO and CO in the melt is what? So for MgO, calculate out, and then for CO, calculate separately. Montesilide, it's olivine, and it says CAMG SiO4. So this becomes CO plus MgO plus SiO2. So 33% 0.33 will be of all. But just calculate out in the same way as you did. Montesalite is olivine, and that is CaMgSiO4. Right?